Somewhere beneath the rolling farmland on the border of France and Switzerland, there is a machine so vast it barely feels real. A 17-mile ring of superconducting magnets, cooled colder than deep space, built for one purpose: to hurl matter at nearly the speed of light and smash it apart. We call it the Large Hadron Collider, and we built it to look back at the first fraction of a second after the universe began. For years, we thought we knew what we'd find down there. We thought the rulebook was already written. But lately, something strange has been leaking out of the data. Numbers that refuse to behave. Results that shouldn't exist. It's as if we've spent our whole lives listening to a familiar song, and suddenly, underneath the melody, we've started to hear a second one, playing in a key we don't recognize. We may be standing at the edge of the biggest rewrite of reality in a century, and what's on the other side of it could change everything we think we know about space, time, and matter itself. If you want to keep exploring the outer edges of what we actually know about the universe, stick around. This is exactly the kind of place this channel lives. Now forget what you think you know about solid things, just for a moment. Let me walk you through what the data is actually saying. Picture a grand piano, fully assembled, tuned to perfection, every hammer and string calibrated so precisely that a single note rings out exactly as intended. Now imagine spending 50 years taking that piano apart, piece by piece, trying to understand not just how it makes sound, but why matter, energy, and force exist at all. That's essentially what particle physicists have been doing since the mid-20th century. We've dismantled the universe down to its smallest working parts, and what we found we call the standard model of particle physics. It's arguably the most accurate scientific framework human beings have ever produced. It tells us that everything around you, this screen, your hands, the air in your lungs, is built from a short list of fundamental ingredients, quarks, which fuse together to form the protons and neutrons at the heart of every atom. Electrons, orbiting those atomic cores, responsible for chemistry, electricity, and the spark of life. And neutrinos, nearly weightless, nearly invisible particles that pass through your body by the trillions every second, leaving no trace at all. Holding this whole structure together are four forces. Gravity keeps your feet on the ground. Electromagnetism powers every device around you. The strong force glues atomic nuclei together. The weak force drives the nuclear reactions inside stars. Elegant, symmetrical. For decades, we believed this picture was essentially finished. There was just one hole in it. The equations couldn't explain why particles have mass at all. So physicists proposed something bold: an invisible field spread across the entire universe, one that drags on particles as they move through it, giving them weight. The particle tied to that field became physics' most wanted fugitive, the Higgs boson. And finding it was the entire reason the LHC was built in the first place. To catch it, scientists had to do something almost violent. Instead of gently disassembling that piano, imagine slamming two of them together at full speed and studying the wreckage, the flying strings, the shattered keys, to figure out what was hiding inside. That's the LHC in a sentence. Two beams of protons, accelerated to 99.99% the speed of light, smashed together to recreate, for a trillionth of a second, the conditions that existed just after the Big Bang. In 2012, it worked. We found the Higgs boson. It was one of the great triumphs of modern science, the last missing piece slotting into place. The standard model, it seemed, was complete, case closed. Except the universe doesn't like to leave things at tidy. As the LHC kept smashing particles together, gathering more and more data, something odd started showing up in the wreckage. Numbers that didn't match the blueprint. Cracks in a foundation we thought was finished. Here's a simple way to picture it. Imagine flipping a coin. A fair coin lands heads roughly half the time. If you flip it 1,000,000 times and it keeps coming up heads 55–60% of the time, you don't need to be a statistician to know something's off. The coin is weighted. There's something inside it you can't see, quietly tilting the outcome. Right now, deep under the French-Swiss border, physicists are flipping a very strange subatomic coin, and it keeps landing wrong. To understand why, meet the muon. Think of it as the electron's heavier, less stable sibling, about 200 times more massive, but otherwise identical in every measurable way. Same charge, same behavior around light. According to the standard model, nature isn't supposed to play favorites between an electron and a muon. Physicists call this lepton universality, a foundational rule stating that the fundamental forces treat these particles equally, no exceptions. But inside the LHC's detectors, When researchers studied the decay of particles called beauty quarks, they noticed something that shouldn't be possible. These decays were producing electrons more often than muons, when the rulebook says it should be a clean 50-50 split every time. At first, everyone assumed it was noise, a statistical hiccup buried in billions of collisions, so they gathered more data, reran the analysis, tightened every variable, and the anomaly held its ground. Think about what that actually implies. If nature is treating two nearly identical particles differently, there's something acting behind the scenes that isn't in our current model at all. Something is putting its thumb on the scale. What could it be? The leading guesses are almost as strange as the anomaly itself, a fifth fundamental force, one that only reveals itself in these extreme, high-energy collisions, or an entirely new, undiscovered particle, something so massive and short-lived that it flickers into existence for a fraction of a second, nudges a muon off course, then disappears before any detector can catch it directly. Physicists have given these hypothetical particles names, leptoquarks, Z-prime bosons, but a name isn't an explanation. It's a placeholder for how much we still don't understand. What's becoming clear is this: the standard model isn't wrong. Exactly, it's incomplete. It might be the top layer of something far bigger and stranger underneath. And it gets weirder the deeper you go. Picture standing at the rail of a boat on a completely calm sea. The surface looks flat, motionless, empty all the way to the horizon. But you already know that stillness is deceptive. Beneath it is a dark, high-pressure world full of movement you simply can't see from above. That's not a bad way to think about empty space itself. For most of human history, nothing meant exactly that. Nothing. Remove every atom, every photon, every trace of matter from a box, and you're left with pure emptiness. But quantum physics tells a very different story. True emptiness doesn't exist. Even a perfect vacuum is, at the smallest scales, in constant motion, particles and their antimatter twins flickering into existence and annihilating each other almost instantly. We call them virtual particles, ghosts that exist just long enough to matter and not a moment longer. Which raises an obvious question: how can something that barely exists have a measurable effect on the real, solid world? Go back to the muon. Like the electron, it behaves like a tiny spinning magnet. Place a spinning magnet inside a magnetic field, and it wobbles, the same way a spinning top wobbles as it loses momentum. The standard model predicts exactly how fast that wobble should be, accurate to 12 decimal places. It's one of the most precise predictions in all of science. But when physicists actually measured it, the muon wobbled slightly faster than predicted. Why? Because the muon isn't traveling through empty space, it's pushing through that churning sea of virtual particles, constantly interacting with them, each interaction nudging its wobble ever so slightly. Scientists have already calculated the effect of every known virtual particle, and even after accounting for all of them, the math still doesn't close. The muon is behaving as though it's colliding with something we've never cataloged, a ghost with no name in our current physics. Sit with that for a second. The physical world you experience is being shaped, at a fundamental level, by an invisible layer of reality that pops in and out of existence faster than we can observe it directly. And now, something extra, something unaccounted for, appears to be swimming in that layer too. This isn't just a missing puzzle piece anymore. It's starting to look like the whole puzzle is sitting on a table we can't see. Here's where things get genuinely difficult to picture. We experience the world in 3 dimensions: up, down, forward, backward, left, right. It feels absolute. Even after Einstein proved that space and time bend and stretch together into a single fabric, it was still, fundamentally, a stage. A flexible stage, but a stage. But what if these anomalies, the misbehaving muon, the lopsided quark decay, aren't just new characters walking onto that stage? What if they're the first real evidence that the stage itself isn't the whole story? Try this. Imagine a garden hose stretched across a lawn, viewed from a window far above. From that distance, it looks like a simple one-dimensional line. An ant crawling along it seems to have only 2 directions to go, forward or back. But walk down and look closely, and you'll see the hose has thickness. There's a second dimension curling around it that was completely invisible from a distance. String theory proposes something similar about the universe itself, that alongside the large dimensions we move through every day, there may be additional dimensions, 6 or 7 of them, curled up impossibly tight at every point in space. far too small for any instrument we built to detect directly. Here's why that matters for our wobbling muon. Think about how strange it is that gravity is so weak. A cheap refrigerator magnet can lift a paperclip against the gravitational pull of an entire planet. That shouldn't make sense. Gravity should be a heavyweight among the forces, unless it isn't actually weak at all. Unless it's just leaking, bleeding out of our three familiar dimensions into those hidden curled up ones we can't perceive. If gravity, or some undiscovered heavy particle, is slipping in and out of those extra dimensions, it would look to us exactly like a ghost. It would appear just long enough to tug on a muon or skew a quark's decay, then vanish back into a geometry we have no way of directly sensing. That's the real weight of this moment. The empty space between your hands right now might not be empty at all. It could be a dense, folded structure of hidden dimensions we simply can't perceive. These anomalies at CERN may not be errors in our math. They might be echoes, the faint sound of something moving through a part of the universe we've never had a way to look at. We built a machine to solve a three-dimensional puzzle, and we may be discovering the pieces have been moving through dimensions we're structurally blind to all along. And that leads to the hardest part of all this. Not that the universe might be stranger than we imagined, but that we might not be built to perceive its true shape at all. Think about how convincing your everyday experience of reality is. You watch the seasons change. You see your reflection age. Everything feels solid, continuous, real. That's not an illusion your brain invented for fun. It's the product of millions of years of evolution. You didn't need to understand 10-dimensional geometry to escape a predator or build a shelter. You needed to know that rock is hard and water is wet. So our entire framework for understanding reality, going back to Newton, roughly 400 years ago, has been built on scaling up or down the world we can directly touch and see. Atoms as tiny billiard balls, the solar system as clockwork. And when we built the LHC, we carried the same assumption forward. Smash the billiard balls hard enough, and you'll find smaller billiard balls inside. But the universe has no obligation to make sense to a brain built for hunting and gathering. These anomalies aren't just puzzles for academics to argue over in a lecture hall. They're a signal that our everyday metaphors have finally run out of road. When a muon wobbles a fraction of a percent faster than it should, we may not be looking at a broken instrument. We may be looking at a layer of nature our biology never evolved to visualize. Push the math of quantum field theory and string theory to its logical end, and something strange happens. The idea of a particle as a tiny solid object starts to dissolve entirely. There may be no small spheres waiting to be discovered at all, only fields. Vibrating, infinite fields stretched across the universe, each one plucking out a note, the way a string produces a tone on an instrument. In that picture, you're not built from tiny building blocks. You're a pattern. A standing wave of interacting vibrations, playing out in dimensions we can't directly sense. That idea unsettles a lot of physicists, because it means the deepest layer of reality may never be something you can sketch on a whiteboard or hold in your hand. What we're seeing in the data from Switzerland might be the faint outline of a structure that is at its core pure abstraction, mathematics operating far outside the boundaries of everyday human intuition. If that's true, then the comfortable solid world you move through every day is a kind of surface illusion, accurate enough to live by, but incomplete in a way our senses were never built to notice. Picture standing on a shoreline that, for centuries, everyone assumed marked the edge of the world. We mapped every inch of the coast. We understood the tides. We thought we'd charted the whole ocean. These anomalies from CERN are like spotting an unfamiliar ship's mast rising over that horizon. Proof the ocean doesn't end where our maps stop. We haven't hit the limits of physics. We may have only hit the limits of what our current tools and theories can reach. This isn't the first time this has happened. Newton gave us a clockwork universe. Einstein revealed that clockwork was really a bending, flexible fabric. Quantum mechanics then showed that fabric was woven from probability and uncertainty at its smallest scales. Every single time we thought we had the final answer, the universe quietly reminded us we were still only looking at a shadow of the real thing. Now it may be happening again. If the muon really is being nudged by a force or particle we haven't identified, if there truly are extra dimensions folded into the geometry of space, then our current theories aren't wrong. They're a rough draft, a sketch of something far larger. And if that draft turns out to be right, the implications are enormous. We might finally connect the quantum world to gravity in a single framework. We might learn the Big Bang wasn't the true beginning, but the collision of larger structures we can't yet describe. We might discover that dark energy, the mysterious force tearing the universe apart at ever-increasing speed, is simply gravity escaping into dimensions we've never been able to perceive. We may not just be hunting for new particles, we may be starting to read the actual source code beneath everything that exists. If this kind of deep dive into the edge of human knowledge is something you want more of, consider supporting the channel through the Super Thanks button below. It directly helps keep this kind of research and storytelling going, so we can keep chasing the truth without distraction. We took the piano apart. We looked beneath the surface of empty space. We questioned the shape of space and time itself. And somewhere in that process, a door opened that we didn't know was there. The question that's left is the one that actually matters. When the dust settles and we finally see reality for what it really is, what does that mean for you?